I will now start with the first session, which tries to answer the question why groundwater monitoring is essential. At first, I would like to introduce why do we, as an institute, as the Soil and Water Resources Institute, feel that we can really talk about water monitoring. So currently, we have installed and operate 3 networks of sensors. The first one is Pineos Hydrologic Observatory, which is located in central Greece. It includes 20 groundwater sensors, 5 meteorological stations, 240 soil moisture sensors, 3 cosmic ray neutron probes. We also conduct biannual groundwater sampling and analysis, and more. In order to give you some numbers, this observatory offer us about 70,000 numbers values per day. Close to Pineos Hydrological Observatory, we have the Pineos Delta networks, in which several conductivity, temperature, depth sensors have been installed in groundwater wells and in the main course of Pineos River. Of course, we have our Metsal observatory, which is situated in Rhodope. We will show you the setup later. And moreover, we perform groundwater sampling and analysis in a wide range of aquifer systems around Greece. We also offer special consultancy on groundwater monitoring for the determination of plant protection products residues in groundwater. But we did not work only with groundwater. We are responsible for the river discharge monitoring for the whole country in the context of implementation of the Water Framework Directive. Also, we were delegated by the ministry, the Greek Ministry of Environment, to install and operate one of the most state-of-the-art monitoring stations in Aliakmonas River, including different technologies of sensors for both river water quantity and quality monitoring, while we are currently installing more operational surface water monitoring stations in the major rivers of Greece. Andreas, the floor is yours now.
Right, thank you. So, before we go on, I'll try to convince you that you do need to monitor. And why do you need to monitor? This is a system, the ecosystem we live and we develop our everyday activities. We develop mining activities, agricultural activities, we have the urban centers. We also develop industry. And we need the industry because simply, on a daily basis, we have to come up with products that we consume. From everyday products up to these little things or the computers we're needing. So all this impose, next please, Vasilis. All these are driving forces that impact on the environment. They give us problems or they get involved to the ecosystems. And Vasilis, as a result, pressures are exerted all over. And these pressures can be seen on the surface in the form of surface runoff that actually gives you an increase of concentrations on the soil, and runoff which ends up in the surface water bodies, or they leach down to the groundwater bodies. They can have problems with the sediments in the rivers and in the creeks. And all these pressures that are imposed in the systems, including the over-abstraction of water, relate to the status that they bring our resources, soil, water, and air resources, with regards to the quality and quantity status. And of course, this next one, Vasilis. And of course, this status relates to the impact that comes to the living organisms in the end of the day and getting into the trophic chain. So we live here, we develop our activities, and we exert pressures on the system. These pressures create the current status, and this current status impact on the living organisms. And because simply we don't want to end up with this kind of impacts like dead fish, what we need to do is we need to respond. So Vasil is the next one. We need to respond, and our response needs to go as early as possible. If we can get response as early as on the driver's level, and next on the pressures level, and avoid to get on the status level or the impact more so, then the result for our ecosystem will be much better. However, in order to respond, we need to know what the situation is. And to know what the situation is, we need to monitor. If we do not monitor, there is no way to know how bad or good the status of the environment is. So monitor, monitor, monitor. Unless we monitor, we haven't got a clue. In the past, my grandparents used to say that I'm fine. I don't need to go to the doctor simply because I don't feel anything bad. And simply because I don't do any blood tests, I'm okay. Okay, a very simplistic thing. When these people realized they had a problem, in most of the cases, it was already too late. So in order to avoid any late response, we do need to monitor and get hands on data on the evolution of a problem right at its beginning. This is the so-called DPSIR approach. You know it. What maybe you didn't know is that behind this, we have a huge tool to monitor and the rationale to monitor. So if we go to the next one, please, Vasilis. Right. And of course, then comes the easy question. Why do we have to monitor? You can monitor for many, many reasons. And when we talk monitor, here and today, we're concentrated on instrumented monitoring, not on a monitoring that we go out once in a month or once in 3 months, perform a measurement and come back. We're focusing on instrumented monitoring, i.e. continuous monitoring. We want to monitor for many, many reasons, as you see here. First one, because we need to assess what the current status of the system is. We need to study the evolution of the system or the resource itself. What does this mean? We need to know an aquifer, is it in good quality, the water there, is it in bad quality, is it overexploited or not? We need to evaluate the impact of the climate change. And this becomes more and more important. Also, we may need to evaluate the impact of anthropogenic activities. You have the industrial unit, you have the agricultural activities, and you need to check whether these are imposing any impacts on your system, especially so in the sensitive environment of coastal aquifers. Also, we need to perhaps analyze seasonal effects and behavior of the groundwater system. What does this mean? It means that not all the systems behave in the same way throughout the year. You have a completely different picture and hydrodynamic evolution of the groundwater system depending on the season when you are monitoring it. And the reason behind it is that every groundwater system is controlled by exogenous factors that need to be taken into account if you want to assess its condition. And you want to assess its condition because simply, if you don't know how it will evolve, and then you cannot forecast its evolution. And to forecast its evolution, you need data. And to update the data, you need to monitor. It all goes back to monitor. And of course, if you don't get yourselves convinced so far, get to the next bullet. The next bullet is about public health. If you don't accept anything else, you need to accept the need to preserve and sustain the public health. You need to protect the environment also. Apart from this, you need to assess remedial and management measures. And if none of the above convince you still, which I'm sure that you are convinced so far, think that we need to harmonize with the European Union legislations and solve any legal disputes. And to do this, you do need to monitor. Of course, if one can sit down for a half an hour, we will come up with a double list or a triple list, and so forth. Vasilis, let's go to the next one, please. And this is not causal enough, but this is an important paradigm of what you can get from monitoring. And mind you that this is not the result of continuous instrumented monitoring, but it's a result of conventional monitoring of one measurement per month. What do you see here? We're in Thessaly in central Greece, and more specifically in the eastern part of the River Pineos Basin. And on the right hand, you see a hydrograph of some 25 to 30 wells. And that's the evolution of the groundwater level for a period of almost 30 years, from 1972 to 2015. What you see here is, depending on where the monitoring well is, you see an evolution of the groundwater level, which shows from minor decline or even stability, like up here, to great decline that can reach even up to 70 or 80 meters in these 40 years. Yes?
Y-axis shows an increase of the level.
Can you repeat, please?
The y-axis shows an increase of the groundwater level.
It's depth to the groundwater level.
Yes,
Okay.
yes.
That's why it shows the increase. It's not the absolute elevation, it's the depth to the groundwater level. I wish it was the other way around and it was wrong. So, even though we're far away from the salinization fronts here, because there's no salinization issue in this aquifer, what you see is a great decline in the groundwater level. The result of this great decline of groundwater level was that we had subsidence, excessive subsidence in the surface. You had damages on the wells, on the road infrastructure, on the railway infrastructure, so forth. And above all, you had a complete damage of the phreatic aquifer due to compression, compaction. What do I mean to say with this diagram? It's not enough only to monitor. You need to do something about the data that is being collected. Because in this case, people were monitoring, even though if they didn't have access to fancy monitoring equipment and instruments and so forth. Still, they were able to monitor, and these were the results. But probably, I'm trying to be polite, they did nothing about it. So the phenomenon kept on evolving and evolving and evolving, especially after mid-1980s, which is the period of time that Greece faced an excessive drought and resulted in excessive groundwater abstraction that progressively led to this issue. So, monitoring is essential, but do something with the monitoring results is even more so. And Vasilis, if we go to the next one, what we're going to see is that groundwater quantity often goes along with groundwater quality. And the red line is the monitoring well, which is located somewhere down here, whereas the orange line, the yellow line, LB99, is a well, a monitoring well, which is located up in this area. So what you see here is again a complete different evolution of the groundwater quality deterioration. In the case of LB99, you see an increased trend of the nitrates concentration, which, okay, is important but not so dramatic. Whereas in the case of SR43, you see a dramatic increase. And the reason behind it is the fact that SR43 is located on the end point of the groundwater system. So very little recharge which is there to replenish the aquifer with fresh water. However, even that amount of water that reaches that point is full of nitrates because it washes off the entire aquifer until it reaches this endpoint. On the other hand, LB99 is nearby the recharge zone, so it gets replenished with fresh water, and therefore you don't see the impact of increased fertilization use in the area. So again, the main thing is you don't only need to monitor, you need to do something about it. Yes?
Just a question, is the aquifer is exploited for human consumption or for,
Okay, the question, so that everybody can hear, is if this aquifer is used also for human consumption. The answer is, thank God, not this part of the aquifer. There are parts of the aquifer that are being used for domestic use, but the parts that are being used for domestic use are safe. They are on the margins of the basin and they don't exhibit this kind of situation. However, in the framework of the Water Framework Directive, the entire basin is treated as it's directed only for domestic use in terms of the limits and the background levels. So, Vasilis, if we go to the next one.
Yes. So, excuse me for one moment. So, we stay in Pineos River Basin, but we focus on the deltaic plain. The business as usual practice for irrigation is not only groundwater, but also the direct pumping of river water through the creation of some mini temporary dams, like the one here. The time series you see here concerns the measurement of electric conductivity in the main river course under a bridge somewhere here. Okay, so we can see that from June 2014 to 2019, it seems that the flow of the river during the irrigation season was such that the impact from the sea is not high. Was not high. We can identify values up to 4 millisiemens per centimeter, but this situation got different for the irrigation periods of years 2020 and 2021. It is very, very obvious that the river flow interruption is so high that seawater is entering at least 4.5 kilometers inland, since we reach easy values of up to 40 millisiemens per centimeter, which is seawater. So you can imagine the effects of this situation in the river's flora and fauna due to the stresses that these very significant changes in water salinity pose. Moreover, you can also imagine the effects of this situation in the groundwater quality of the phreatic swallow aquifer. I can guarantee you that such a situation can only be captured with high frequency systematic monitoring based on sensors. We stay in Pineos Delta. Here we don't see data from sensors, but we see data from several groundwater sampling surveys in this groundwater monitoring network. Okay, we can see that the median values of nitrates do not vary very significantly, but we can see that the maximum values have very great variability. One could say that performing 6 groundwater sampling surveys in 2 years is too much. The usual practice is to have 1 or 2 groundwater sampling surveys per year. But you can see that the maximum values changing a lot. And these maximum values are the ones that indicate to us to take measures, to take actions. Pretty similar picture we take for ammonium ions. We can see a great variation in the maximum values. Andreas, please.
Right. Now, we're moving south of Pineos Delta. It's Pineos Delta, then you have Kisavos Mountain on the south, and on the southern part of Kisavos Mountain, you have this basin, which is our pilot area, the Aya sub-basin, which hosts the Pineos Hydrological Observatory. Now, what you see here, out of 2 specific and very, very characteristic monitoring points that are equipped with CTD sensors, that is, sensors that measure conductivity, temperature, and water level, water pressure, to be more correct, on the same time. What you see here, let's go first on the top one, which is located, is it so? Yeah, which is located on the northern part of our monitoring network, which is the transition zone from the mountains to the plain. What you see there is a very significant and very distinct trend between the variation of water level and electric conductivity. On top of that, electric conductivity is the red line, and water level is the blue line. And on top of that, you see a great correlation between the precipitation events and the evolution of the water level. Same goes for the other point, which is located on the plains. What is apparent, of course, here is that the patterns are completely different. In this case of the transition zone, the evolution of the groundwater level is inversely proportional to the evolution of the electric conductivity. Whereas, in the case of the monitoring point in the plains, the evolution of the water level is more or less proportional to the evolution of the hydraulic conductivity. And there is a reason behind it. We'll see it in the next slide. What needs to be shown here, though, is that it's very easy through the electric conductivity to have an idea of the evolution of groundwater quality in your area. And why is this important? Simply because electric conductivity can be very, very easily measured and monitored through a very cheap and very reliable and effective sensor. Here, on the green line, you see the results on the bullets of nitrates concentration in the very same monitoring points following a conventional groundwater monitoring campaign, which means that we went out there, collected groundwater samples, got in the laboratory, and Vicky analyzed the samples to come up with the concentrations. What you see here is concentration values, and if you plot them with a line, with you see that there is a follow on the trend. You don't see an exact pattern, like one line falls on the other, which you don't expect to see ever. However, you see that there is a correlation between them, which simply means that knowing what's the evolution of a very easy parameter to follow continuously, like electric conductivity, can give you a hint on what you expect on the nitrates concentration. And please try and think what you can do with this kind of picture if you get to remember what you've been told in the previous days of this summer school. So the potential to explore the evolution line of a continuous monitoring system and get indirectly results on the expected evolution of a specific constituent in your groundwater is there. The more data you have, the better and the more reliable the correlation will be. But the idea here is, and this is what I want to show you, is you can really get an evolution pattern that is going to be very, very crystal clear. If we go to the next one, please.
So let's go now to the Medsal pilot site in Rhodope in Greece. We have installed there three CTDs, conductivity, temperature, depth sensors, as I will show you later. The one of the wells irrigated by the yellow arrow is pretty close to the sea and very close to a lagoon. So one could expect that as we abstract water during the irrigation period, electrical conductivity would increase. But no, we can see that salinity is decreasing as we abstract the groundwater. This situation indicates us the complexity of the aquifer system. So we have some aquifer layers of high salinity, but of low groundwater potential. These layers tend to be exhausted, to deplete as we abstract the groundwater. As we abstract the groundwater, and aquifer layers of higher groundwater potential and of lower salinity provide us with groundwater of higher, let's say, quality. Imagine how non-representative could be a single groundwater sample in this groundwater well. If we took a groundwater sample during late June, let's say, somewhere here, we could get a conductivity value of about 4,000 microsiemens per centimeter. While taking a groundwater sample at the end of irrigation period, somewhere here, would result to about half salinity. Also, please have a look to the lower graph. We can see two patterns which are very impressively and almost identically reproduced for both monitoring periods, for both monitoring years. After irrigation season, groundwater temperature is decreasing and electrical conductivity is increasing. But at late December, water temperature starts to increase again and show salinity with higher rate. All this situation reveals to us complex water mixing patterns of groundwaters, which are definitely not random. All these results cannot be achieved only with one or two single groundwater samples per year. So let's go to the next slide. Here, the other groundwater monitoring well, we can clearly see very high EC variation, electrical conductivity variation during the abstraction period, ranging from, let's say, 3 to 12,000 microsiemens per centimeter. Again, we notice some very saline aquifer layers which are of lower groundwater potential compared to the lower salinity layers. And again, we identify complex water mixing patterns which are very reproducible for the two monitoring years. We can see that after the end of irrigation period that we have a mild decreasing trend in salinity, while from early to middle January, we have a very rapid decrease in salinity, and then it is almost stabilized. We also have the decrease in uh, water temperature. Again, it is very obvious that these results cannot be captured with single groundwater samples collected 1 or 2 times per year. Let's see the third groundwater well now. The fluctuation of electrical conductivity is totally different from the other two groundwater wells with lower EC values. But again, we cannot identify some reproducible patterns in groundwater electrical conductivity and temperature variation. Let's go now to Salento. This is a very good example of the combined implementation of monitoring in fixed positions, in fixed depth, and groundwater depth profiling, which is also known as logging. The term groundwater depth profiling describes the procedure of monitoring parameters such as electrical conductivity, salinity, not only at a single depth in the groundwater well, but for the whole well depth in order to capture the fluctuation by depth. In this case, we can identify the features of the transition zone between fresh water and salt water, but also with a single pressure transducer, we can have very detailed information about groundwater level, which does not vary significantly, but we can see that it indicates a decreasing trend, which is very significant from the water resources management perspective. This result cannot be, again, I mentioned this, cannot be gathered only with single monthly, biannual measurements. So we would like to thank you for your attention.
Thank you, Vasilis, and I think we can quickly move to the next.
Yes, Andreas, very quickly.
Because we're already running behind schedule, I'm afraid.
So the second session, the second session concerns the principle of sensor-based groundwater monitoring networks. And let's have a look at the principles that we have to keep in mind when we design groundwater monitoring networks that are based on sensors. There is a set of parameters that we have to be as accurately as possible defined in order to conclude with the network setup. So we have to identify the most significant zones to be monitoring in a salinization prone aquifer, the most significant parameters to be monitored, the groundwater well features and equipment that allows the most effective monitoring, and finally, we have to define the monitoring frequencies in the alerting SIMs for each monitoring target. So each one of us is unique and this is the way that we have to think about aquifers. There are unique combination of geological, hydrological, geomorphological, land use, climate, and water resources management conditions. So generalizations have to be avoided, but in the same time, they have to be kept at basic rules and criteria that need to be adopted and followed as a line of thinking and conduct of good practices. We have to specify criteria for each case separately. We have to specify monitoring protocols. We have to take into account the complexity and non-linearity of groundwater salinization, which needs significant expert knowledge. And finally, the motto is to complete knowledge, we need monitoring. But to set up monitoring, we need knowledge. These are two interlinked and interdependent aspects. So, designing and installing a sensor-based groundwater monitoring network is a complex task that cannot be accomplished only by one or a few persons. So, the successful monitoring goes through close collaboration and interaction between scientists, stakeholders, technicians that work together in order to answer the key questions. Where to site the sensors to best capture the salinization transition zone and thus effectively and accurately monitor it. Very essential hydrogeological characterization provides us the most critical and fundamental data and the rationale required for designing the groundwater monitoring network. Without this, and without considering uncertainties and limiting factor on this, the monitoring network will fail. So finally, these are the 5 topics that have to be addressed in order to have a successful network. So first, we have to identify the salinization phenomenon. Then we have to define the monitoring frequency. We have to define the sensor maintenance and fieldwork that is required. Also, we have to identify the functions to be monitoring, and last but not least, to have the alerting as a valuable optional asset of monitoring, and if we need it. Andreas, please.
Okay, I'm going to continue only under the provision that we have already convinced you that monitoring is essential. Are you convinced? Okay, I see some yes. So we go right. In order to identify the salinizations based on monitoring data on the sensors, we need first of all to develop a clear idea of what we need to achieve from the monitoring network. You cannot have a single monitoring network to cover everything. Its network can cover a specific scope. Nobody can develop a network that will cover all the needs of the world, simply because the type of instrumentation, the depth of instrumentation positioning, the frequency, the selection of the wells to be monitored, and so forth, depend strongly on the exact target of the monitoring exercise. So, no monitoring network for everything. You need to define clearly the scope. And to define the scope, of course, means you have to make decisions. Many decisions. And to make many decisions, you need many data, which gets us back to monitoring. You need monitoring. And to proceed, you first need to select the monitoring parameters. What exactly do you want to monitor? Which exact parameter? Monitoring in general is like a cloud, but the cloud is only nice to save data. It's not a good thing to have in your mind when you're going to set up a network. You have to be very, very clear there. What do you want to monitor? So, monitoring parameters, appropriate sensors. Not all sensors are appropriate for monitoring a specific parameter. There are many, many things, a long catalog of ideas and of specifications that need to be taken into account in order to make the correct choice. Of course, you need to find and select the appropriate wells. So, 3 different things. Decide on the parameters that need to be monitored. Decide on the appropriate instruments that you're going to use for these parameters. And third, decide on the appropriate wells where these sensors will be installed. And if I want to be more detailed, I will put a fourth parameter there. Decide on the depth these sensors will be installed. And let's see the next one, please, Vasilis. Right. I'll freshen up your memory from the previous 3 days of the summer school. When we're talking salinization, there are 2 basic approaches. It's a sharp interface approach, where what you see is that there is a basic assumption that between salt water and fresh water, there is a surface on one side of which you have the fresh water, on the other side of which you have the salt water. Does this exist in nature? No. But it's a simplified version of the reality. And what are the essential, what's the essential thinking behind it? That the fresh water and the groundwater are immiscible fluids, which means that they don't mix with each other. Second one is that the flow of the freshwater aquifer is horizontal. The flow is horizontal. You don't have any vertical components of the flow. And the salt water is either immobile or mobile, but again, if it's mobile, it's going to be horizontal flow. So this is the principle of the sharp interface for salinization. And apart from that, we have the real thing, which Vasilis is. We'll go to the next one. Right, thank you. The transition zone concept, where you have the real thing, the reality. And the reality is that fresh water and salt water are 2 miscible fluids, so they mix with each other. And mixing with each other, they create a transition zone which has vector flows from bottom to top and circular flows in parallel or in accordance to the thermodynamic rules. And if we want to be more detailed, I'm going to change the camera for a while. Allow me. Okay. When we're talking about salinization, there are 2 different things. If this is the sea, can you see this? Is it visible? Or the marker is bad?
We can see in the.
It doesn't show on the screen. Eh? Yeah, okay. Never mind. I will describe it. You can have 2 different things of salinization, 2 different basic modes of salinization. Okay. The one mode is the typical salinization like this. You have the seawater intrusion like this entering inland the freshwater domain, and you have a so-called upconing. And upconing is the effect of salinization when it occurs from the lower parts of the aquifer towards the upper part of the aquifer. And you can experience this if you think like the inverse situation of an obstructed groundwater well. So, if you have an obstructing water, an obstructing groundwater well, then you will have a depression cone, and the depression cone goes something like that, and in the middle you have the abstracting well. All right. In the effect of the upconing, exactly because you drop the hydraulic head within the well, so you have a lowering of the groundwater level. As a result, if you happen to have salinization, seawater underneath, the seawater will start progressively to increase its level simply because the hydraulic equilibrium between fresh water and salt water is disturbed. So the more you remove fresh water, the more the salt water will come up and up and up, giving an effect like a belly. Okay? And this is the so-called upconing. And why is this important? Because it's a completely different geometry and evolution than the typical evolution of the salinization, the seawater intrusion, and needs very, very careful consideration when you decide to monitor this phenomenon. That's why you need to differentiate seawater intrusion from upconing. Okay? Vasilis, next one. Good. So, apart from groundwater level and electric conductivity, which are the very first parameters that comes into one's mind when you think monitoring, especially in the case of salinization fronts, there are also sensors that allow you to monitor other parameters like temperature, pH, dissolved oxygen, redox potential, turbidity, nitrates, and other specific ion selective electrodes that give you monitoring the results of specific parameters. And it's not necessary to be ion selective electrodes. It could be also new spectrophotometric approaches that operate in situ in the field. Of course, they're very expensive, but very, very accurate. So apart from electric conductivity and groundwater level measurement, you can have temperature, pH, ORP, oxygen reduction potential, that is, and a list of others, as I show here. Do you need everything? Not necessarily. Every time you need to decide which one you need. Just saying that I go in the supermarket and I buy everything and install it is not a solution, because each parameter costs a specific amount of money. If it doesn't offer you something, you don't need to install it. The only difference here is if you decide to go for groundwater level or electric conductivity, 99.9% of the cases, you are going to have temperature measured by all means, simply because groundwater level and electric conductivity, as the other parameters as well, are temperature dependent. So to give you an accurate result, they are measuring also the temperature of the water. Now, whether they are going to give you this measurement or just use it for compensation reasons is another story. But temperature is always measured. So let's go to the next one, Vasilis, please. Right. Just to remind you two different things. You have two basic types of aquifers. You have the phreatic aquifers or the unconfined aquifers. Phreatic is a specific condition of unconfined aquifer. And you have the confined aquifers, and the specific condition of the confined aquifer is the artesian flowing well in such an aquifer. Now, what is the great difference? The great difference is that, as you can read, in the groundwater level in an unconfined aquifer, do we have any?
Maybe someone has just a microphone.
Okay. So, if we're talking about an unconfined aquifer, then we're talking about the water table under zero pore pressure within the material, which means that you dig a well or you drill a well, and where the water is the free water surface. Like, for instance, We don't have balance defined here. Yeah. For instance, if you build a well here, then we are going to have the water level in this elevation, and it will not change. Whereas if the confining unit is here, drill a well like this here, the water level will rise up to this point. And this is artesianism, is a very specific case of the confined aquifer. So it's an imaginary surface where the water would have risen if you drill a well, because of the pressure that is exerted on the aquifer because of the confining units. Okay, so I just remind you the two basic differences because we are going to be reading it the next slide. So, Vasilis, please. Next one, right. Good. So, the very first parameter to monitor is the groundwater level. And the groundwater level is measured with a device which is called pressure transducer, or PT. We use the term here. And how do these things measure? This is a typical device. And the size of this device is something like that. Okay? It's 10 to 12 centimeters long, and the diameter is less than 1 inch. Not all of the sensors are this small, but you can get as small as this. So this simple sensor can store up to 12 or 13,000 sets of data points, which means temperature and groundwater level, pressure level. So what does this measure? It measures the PI, the relative gauge pressure. That is the pressure that is exerted on the sensor because of the water level above it. So you have the sensor in the water, and there is a water column above that. And what it measures is the pressure of this water column. Okay? So this is the relative gauge pressure. How does it measure? Each of these sensors has a diaphragm on one edge, which is very sensitive to pressure. So the pressure that the hydraulic pressure, the mechanical pressure that is exerted, diaphragm, is converted to an electric signal. And this electric signal is converted to pressure. And this pressure is then compensated for temperature. And this compensated for temperature pressure is given on your reading. All right? Is it simple as that and we're done? Unfortunately, not. There is another compensation that is required. And this extra compensation has to do with the barometric pressure. Okay? And what this has to do with the measurement of the pressure? It has to do with the fact that if you're measuring the pressure that is exerted on a gauge because of the water column alone, you need to compensate this pressure for the barometric effects. So you need to make sure that what is being measured has been cleared by the changes of barometric pressure, that is atmospheric pressure. And this is important only or basically when you are monitoring in confined aquifers. If you are monitoring in unconfined aquifers, this becomes negligible. But in confining units, this is very important. So in the case of the simple measurement of groundwater level without the compensation of barometric pressure, what you get is the mixed effect of barometric pressure and the pressure exerted by the column of water. To overcome this problem, there are two ways. You either connect your sensor with a cable up to the surface, and this is hollow, So it equilibrates on the back side of the diaphragm the barometric pressure to the back side of the diaphragm, and this is the vented tube, so-called, or you measure the pressure without compensation of barometric pressure. You measure the barometric pressure on the surface through another sensor, and you compensate the measurement so that you come up with a clear groundwater level data. So let's go to the next one, Vasilis. Right, just to have it in mind, because this is somehow confusing in some cases. Always, when you refer to groundwater level, you refer to a specific datum. And normally this datum is the mean sea level, okay? So what you have is the elevation head, and the elevation head is typically the absolute topographic elevation where you position the inlet of your pressure transducer. And on top of that, where you have the groundwater level, and the groundwater level will be the altitude from the datum up to the free surface or the confined piezometric surface of the aquifer. Now, the point from where you position your pressure transducer up to the groundwater level is called the pressure head. And essentially, this is part, hear me out, this is part of what the pressure transducer measures. This column. And why is just part of it? Because, as I told you before, this water column, which exerts pressure on the diaphragm of the pressure transducer, is relating to the water column, and it's inversely proportional to the density of the fluid. So it will make all the difference of the world if this is salt water or fresh water, simply because fresh water has an average density of 1 cubic meter per cubic centimeter. Okay, one, and salt water is 1.25 or less. Okay, so imagine this, how big a difference it makes. But this cannot be distinguished by the sensor. The sensor just measures pressure. Pressure is the result of the column and the density of the fluid. So you always need to compensate for the density in order to be sure what you're measuring. So you also need to know for that what you are measuring here with the pressure transducer again relates to temperature and electric conductivity. Okay, is this clear so far? You need to be very, very careful with this. So Vasilis, let's go to the next one.
Yes, so let's move now from pressure to electric conductivity. So most of you probably are familiar with this parameter. For those who are not, electrical conductivity is the parameter that quantifies the ability of a medium to conduct an electric current. It's so simple. So EC measurement is based on the transmission of electric current through water. For this, electric voltage is applied between two electrodes in contact with water, and the drop of this voltage measures the water resistance. Voltage drops depending on the electrode area, the distance between the electrodes, and the salt water content. So when we have a sensor, the electrode area and distance are stable, are not changing, and the only factor that changes is the water salt content. So when an electrical potential is applied to an aqueous solution containing ions, positive ions migrate towards the cathode, and the negative ions migrate towards the anode. Electrolytic conduction occurs mainly with salts in the solid, liquid, or dissolved state, and this involves the migration of ions. Fresh natural water has a very low EC value, which increases as the concentration of total dissolved solids, this TDS parameter in the water increases. So, technically, EC is the electric conductance per unit of distance. It is expressed in Siemens per length unit, and it is inversely proportional to the electric resistance. Electrical conductance and electrical conductivity indicates the same parameters. So since EC can be highly variable with temperature, the scientists established the term specific electrical conductivity, which is the EC of one one centicubic cubic meter of a solution at 25 Celsius degrees. In this way, we can avoid the effect of temperature in EC measurements and have, let's say, a standard basis to compare. Most, if not all, the modern instruments make an automatic temperature compensation. But please have in mind that the compensation is based on standard solutions, usually potassium or sodium chloride solution, which is not accurate for waters with a far different chemical composition. For example, let's say calcium sulfate type or acid mine waters. The relationship between EC and TDS in dilute solution is direct. Nevertheless, when the salt concentration reaches a certain level, electrical conductivity is no longer directly related to salt concentration, and as the solution concentration increases, the slope of the relation slightly decreases. A few empirical relationships exist to convert EC in TDS for natural waters with EC between 100 and 5,000 microsiemens per centimeters. This equation that you can see here is one of the most widely used in the literature. Of course, this factor, this 0.65, can change. As previously explained, the influence of different solids on EC is not equal. Consequently, the same EC values may represent different water chemical composition and water types, in turn represented by different TDS values. So, let's see now how these electrical conductivity sensor data from the sensors can be implemented. The first case is the groundwater depth profiling, as we introduced in the previous presentation. This is a very, very nice example coming from the area that you are now in Salento. for which the transition zone between fresh water and salt water is captured from time to time. Please have a look on how salt water depth can vary from 85 to 130 meters, and imagine how valuable this information is from the groundwater management perspective. Of course, in order to implement profiling, we have to be sure that our wells are open to the entire aquifer, crossing zones of horizontal flow, and in absence of vertical currents. The second concept is capturing the temporal variability of EC in a single point as a result of hydrodynamic evolution and or well exploitation conditions. This is very significant from the operational perspective of water resources management, and when our monitoring is focused on water resources protection, a concept that we will introduce to you in the next slides. Last but definitely not least is the concept of electrical conductivity spatial variability. This old-fashioned but very informative map demonstrates the contour lines of equal EC values for the beautiful island of Limos in Greece. This spatial distribution is very useful in order to identify trends and links that are related to hydrodynamic evolution of the aquifer system. So we can identify information such as areas with higher potential of seawater intrusion or areas for which other salinization processes have to be identified. Andreas, please.
Thank you, Vasilis. So far, we've seen groundwater level and electric conductivity. And we said that all of the above, plus other parameters that can be monitored, always come as a set with temperature. And this is simply because all of the measurements are temperature dependent, and we need to compensate for the exact temperature we have in the solution. So temperature alone is a parameter that is very, very useful. And you can find it as a standalone sensor or as a sensor which comes in a pressure transducer or a CTD, which is conductivity, temperature, depth, which is pressure. So let's see what you can get out of the temperature itself. You can get temperature profiles, depth profiles. And these temperature profiles are perhaps much more reliable than the electric conductivity or TDS depth profiles in recognizing salinity stratification. Also, it can give you reliable information on the ambient temperature, even in the case of wells that are being cased. This is because temperature can be transmitted with two different mechanisms. One is convection and the other is convection. So convection is simply when you touch your hand on the hot surface and you get burned. And in this case, you have an aquifer, you may have a casing, and this is the only place you can monitor. And temperature can be conveyed through the convection mechanism from the outside part of the aquifer to the inside of the well to the inside part of the well. Whereas if you are monitoring electric conductivity, you don't have this option. You have to depend on casing, which is open opposite all different aquifers or layers of the aquifer system in order to get the signature of the electric conductivity. So temperature in this aspect is much better because whether you have a filter in the casing of your well or not, you're going to get the signature because of the convection mechanism. Also, the ambient temperature correctly represents the structure of the aquifer. for the very same reason. Whether you have a water which is a monitoring well, that is, you don't have any abstraction, or whether you have a well which is being abstracted, if you perform a log, a temperature log, you are going to get much better and integral results than if you perform the same log for electric conductivity for the reasons I told you before. Provisions, however, you can get all of the above, given that the wells are in such a condition that you don't have any anomalous heat gradient in the region, and that you're logging conductively, you are logging from top to bottom so that you don't get any disturbances from the sensor to the water column. And this is a typical thing you always have to do. You start from the top to bottom to avoid any disturbances and turbulence, which will distort the results. In any case, what you have to remember is that temperature profiles, either logs or spatial distribution, will always give you better results. It will give you a better resolution in cases you have fractures. It will give you a better resolution in cases you don't know exactly where the filters of the aquifers are. These are the good parts about temperature. And of course, the other good part is that it's way of lower cost than any other sensor. What is the bad thing about it is that you cannot quantify the effect of temperature and convert it to electric conductivity easily. It's very difficult to do such a thing, right? So remember that temperature is very useful because you have the convection, but also you have the advection. And the advection means that you can capture the changes of the temperature, the basic flow mechanisms, hydrodynamic mechanisms that control the evolution of an aquifer system. That's why performing a temperature profile nearby the recharge zone of the aquifer will give you very good results on the evolution. Same goes for a temperature profiling close to the discharge zone. Let's go with we've talked so far about pressure transducers, electric conductivity, which can be converted to dBs with all the problems that Vasilis explained, and temperature with all the constraints I explained. Apart from those three basic things, parameters, what you can also measure easily is the pH, which is the negative logarithm of the concentration of hydrogen ions. And practically, this is a measure of the alkalinity or acidity of a water solution. And you do this with an electrode that contains, it's a combination of a pH-sensitive electrode plus a reference electrode and a temperature electrode to give you the correct value. You can also measure dissolved oxygen, and dissolved oxygen is characteristic of the recharge and the discharge zones. It can easily be correlated to a number of factors, including the recharge or discharge. This in the fresh water can vary to any value from 7 to 10 milligrams per liter. You can measure it as a degree of saturation, as a percentage of saturation, or as a concentration. Now, how this is measured? This is measured with optical sensors nowadays, which are very reliable. They don't drift, and they're very accurate in measurements. pH, on the other hand, needs to be calibrated in frequent intervals. Depending on the exact electrode, these intervals may vary from 1 month to 6 months. 6 months is maybe exaggerated. It's too long. And last but not least, you have the ORP, the oxygen reduction potential electrode, which measures the overall attitude of a solution to act as an oxidizing or a reducing agent. What you have here is a measurement that gives you the net oxidation or reduction status of your water solution. And this is a result of all the kind of reactions you have in your water solution. And this These reactions can be seriously affected when you have salinization phenomena. Now, the important thing about the ORP electrodes is that they're very, very sensitive. Overall, it's a very, very difficult measurement, and you need to be aware that the level of stability, the time of stability is very, very low. So you're looking at calibration intervals that, as a practical rule of the thumb, would not extend more than 1 month in the best case. So you're talking about a difficult measurement which has a lot of drifting, needs to be repeated pretty often. Next one, please, Vasilis. Right. Now, normally these three sensors and parameters are being monitored because we tend to relate them with the study of the pollution status of a groundwater or a surface water body. But in coastal aquifers, it is interestingly enough linked with mixing processes. So mixing of fresh water with salt water gives you all sorts of interactions and reactions, as Professor Tsunade told you the day before yesterday. And this is very, very important because indirectly you can check and monitor the salinization from monitoring also these parameters. So the transition zone is a very dynamic hydrogeochemical environment where all sorts of reactions, as Professor Tsunade explained, take place, and this can be indirectly monitored, again, I stress, through these parameters. So what you need to remember about this is that the salinity variations cause chemical disequilibrium and renewal of water-rock interactions that involve changes in temperature, changing the chemical composition, alkalinity, pH, DO, and ORP status. Vasilis, next one, please.
Now it's my turn, and I would like to introduce you two concepts that support us to decide where to monitor, in which areas to focus. So the first concept is the resources monitoring. Under this concept, we consider the aquifer system as a whole, since we target to capture and evaluate the total effects imposed on groundwater by natural and our human-induced practices. This concept allows us to detect temporal variations in groundwater storage and flow, in groundwater quality for the whole system, and therefore it gives us the ability to plan long-term and large-scale management actions and assess the effects of their implementation. The second concept is the protection monitoring. Under this concept, we concentrate to zones of influence of well-filled systems or close to abstraction wells to control the side effects of their operation. In this way, we monitor the monitoring results refer to the local vulnerability and risk of the concerned sources. The risk can be moderate or high, depending on the prevailing groundwater use and or financial, social, and environmental impact upon its known availability. For example, a moderate risk, let's say, can be defined for irrigation sources, and high risk should concern potable consumption. Ultimately, real-time monitoring should allow adapting timely actions to manage the increase of groundwater salinization. What I previously mentioned is summarized in this very informative diagram. I will not get into details since we don't have much time. What I would like to add here is that for groundwater resources monitoring, the distribution of wells in the aquifer has to be homogeneous. Let's continue with this diagram. It is very critical for resources monitoring to locate wells in the zones of horizontal flow. This is very, very critical. These wells have to discard the recharge and discharge areas in order to avoid vertical velocity components of flow. For protection monitoring, it is critical to locate monitoring wells within the zone of influence of the well field. Let's now summarize some simple rules for both types of monitoring. We have to define the key targets, to delineate the study area, to take as much information that we have for the candidate groundwater wells. We have to be sure that we have enough space in the groundwater well that can accommodate our sensors. And also a very, very critical thing is to ensure the safety of the instruments. Also, they should be easily accessible. And specifically for resources monitoring, we have to, as I said before, avoid areas of dominant vertical flow, avoid monitoring wells tapping several aquifer units, avoid the obstruction wells, and define transits perpendicular to the coastline. Regarding the installation depth of groundwater level sensors, these pressure transducers that Andreas introduced before, we have some practical but essential rules. The basic goals is to place the sensor at a level that ensures that water will not drop below it. We don't want the sensor out of the water. We will take no data. So we have to collect as much historical data as we can. We have to analyze it in order to capture the trends and constrain to time window reflecting the expected conditions. We will not go, let's say, into pre-exploitation values, which might never be restored. This analysis will help us to define the maximum anticipated water level fluctuation with extra cares, of course, to abstraction wells, for which water level fluctuation can be very, very high, up to several tens of meters, let's say. Please keep in mind that we usually have higher water level fluctuation inland and lower at discharge zones. We have to define the transition zone in order to avoid installing the groundwater level sensors there, since, as Andreas mentioned, the higher water density affects measured pressure. You cannot install a sensor in wells which does not have enough space to accommodate it, as I said before. So please investigate the well casing and the pumping system and calculate available installation space. Extra critical, please carefully define the required pressure transducer resolution and operational pressure range. Especially the overpressure can damage your sensor. Andreas, please.
Right, my turn. What about the installation depth of the pressure transducers? This is a very complex diagram, and I'm not going to spend a lot of time on this to elaborate. You'll have this in your notes, they're already uploaded in Teams, but what you need to keep out of this is that depending on what you want to do and when you want to, what you want to monitor exactly, you have to follow different rules. But there are some common rules to follow. One, study carefully historical data if it's available. If it's not available, you simply have to go and ask for experts' knowledge. Always, in every area, you will find an expert, and if it's not an expert, it's going to be a person that knows more or less what's going on with groundwater level fluctuation, and this information may come very, very handy and important deciding which depth you want to install your pressure transducer for water resources monitoring. That is, if you focus on resource monitoring rather as to the other type of monitoring that was in sunlight. In this case, therefore, what you have to check is again, what is the pressure transducer depth that you need to install, taking care of the fluctuation and taking care also of the pressure range. You don't want your pressure transducer to get out of the water column. You don't want your pressure transducer to get deeper than the range it can support. Always keep in mind that pressure transducers come at a different operating range. You can find pressure transducers that operate from from 0 to 1 meter up to 0 to 100 or 150 meters. You select what you want based on the amplitude of the groundwater level evolution in your particular case. You don't want to go to 1 to 150 meters simply because the resolution you're going to have as the accuracy is going to be reduced compared to a pressure transducer that has an operating range of, say, 0 to 10 meters. So be sure that you know exactly what you're dealing with, and based on that, you select. And always you need to go back and check on the data. Check whether you have correctly positioned your sensor in the well, and therefore it's not getting overpressured or outside the water. Vasilis, next one, please. Right. Protection monitoring, the other type of monitoring. Here, the rationale is a bit different. And it's a bit different because the focal point is different. In the resource monitoring, what you have to keep in mind is that you don't expect many very high fluctuations simply because you're focusing on monitoring wells that are not being used for production of water. Therefore, the annual fluctuation is bound to be restrained to a few meters. And of course, the closer you go to the endpoint, to the coastal zone, the less is the expected fluctuation. In this case, on the protection monitoring, we expect to have much greater change of groundwater level between the extreme sides. Okay, and the reason behind this is that most probably you are going to install your sensors either in the production well or in a well which is very close to the abstraction well, that is within the radius of influence. Because of this, the fluctuation is bound to be much, much higher. Again, and more importantly, critically here, you need to make sure that the operation range is sustained within the limits of the aquifer, or in other words, what you select as a sensor should be falling in the range of what the aquifer is expected to behave like. Typical rule of the thumb goes to the pressure transducer depth should be at least 2 meters lower than the minimum groundwater level registered in the well field, and the pressure transducer should be close to the pump inlet. In any case, this way you're going to make sure that you're not going to be missing any measurements. theoretically speaking, the depth of the pressure transducer should be even below the pump inlet, so that we make sure that you're not going to lose absolutely anything in terms of measurements. However, practical terms, if you are installing your sensor in the abstraction well, and you don't have a piezometric tube in the abstraction well, there is no way you can install your pressure transducer underneath the pump inlet. Dangerous, and you don't have the angle. So, as a practical rule of the thumb, if you manage to install your pressure transducer at a depth pretty close to the pump inlet, not above it, you are bound to be okay and safe in terms of making the appropriate measurements. Let's see this next one, please. Right. Practical rules which summarize what I told you before. Statistically analyze the historical data and constrain to the time window of the period of time you expect to find from this point onwards. There is no use to analyze any historical data which dates back 50 or 60 years, simply because you are not dealing with this kind of conditions. If you're lucky enough that these conditions of 60 years ago reflect the current conditions, then do it. Otherwise, go for the time period that reflects the conditions you expect to have in the near future. And of course, this needs to be reviewed every few years, depending on the evolution of your system. Analyze the electric conductivity profiles if available. Why you want to do this? Simply because we are talking about groundwater levels, and you need to be above the transition zone. You need to be in the fresh zone in order for the groundwater level to be representative of the fresh water, therefore real water level, and not involved in the density variability due to salinity. If you happen to go and measure groundwater level in the transition zone, then you always have to account for it and compensate, so that what you measure, you know that it's correct and it's not a conurbation of pressure head and pressure gauge, which mix together without being able to distinguish. Seek local experts' knowledge on the hydrodynamics of the transition zone geometry. This is clear, I think. Select the upper part of the beginning of the transition zone and an AC range of about 3 to 4 millisiemens per centimeter. No need to go for something which is lower, simply because you're not going to be effectively monitoring any transition zone. We're talking about salinization due to seawater intrusion or any other mechanism that relates to the creation of a transition zone. So, in order to be able to capture the transition zone and its evolution, a practical rule of the thumb is go for a 3 to 4 millisiemens per centimeter. And this has to be assessed as the depth, with regards to the depth, over the period of full recharge, the end of the recharge period, so that you'll be able to capture the entire evolution. So you assess which is the correct side depth based on the criteria set before during the end of the recharge period, in order to make sure that you will be able to capture the entire evolution of the phenomenon. At least 2 meters lower than the radius of influence of the well field or pump intakes for the abstraction wells. And you don't select wells where the maximum electric conductivity value at the bottom of the well is less than 3 millisiemens per centimeter. Again, if you're focusing on capturing the phenomenon. Otherwise, you can just decrease. Define the location of the transition zone position at the end of the recharge period, as I told you. And it's always useful to calculate the 10th quantile of salinity across the transition zones and see where this depth corresponds to based on logs that you have performed, if available. If not available, of course, you cannot do it. And another option would be to run analytical solutions to select where the 10th quartile is. So next one, please, Vasilis. I told you about analytical solutions. There's a list of alternative approaches to analytical solutions, more sophisticated, less sophisticated, that are working on a sharp interface or a transition zone interface. This is a typical solution, a typical set layout of a solution where you have an inclined base of an unconfined aquifer with a specific inflow and the salinization front. Solving this equation for different results mounts, you can get different salinization fronts, and based on the results, you can decide where to site. This comes very, very handy in cases you don't have historical data and you don't have logs. Solving this, following this exercise can give you a hint on where you best site your sensors, rather than going, defining a place without having any clue at all. Next one, please, Vasilis. Right, and you have also in your handouts on Teams a list of selected literature for this kind of analytical solutions. Let's go to the next one, Vasilis. Right, your turn.
Yes, my turn now. There is a very useful guide here that supports us in selecting the installation depth for easy monitoring for electrical conductivity under the resources monitoring concept. What I would like to focus on is to use the expert knowledge. Aquifers are complex, unique systems, as I said before, and the expert knowledge is always more than welcome. Moreover, when you have the opportunity to carry out electrical conductivity depth profiles, please do it, since it will give you the real situation, thus reducing the risk of installing the sensors in a not so appropriate position. Applying the theoretical approach, like the Gibbon-Helbers law, is a complementary or an alternative solution, but having the real data, the real situation, is much more preferable. This is the diagrams that aim to support the selection of the installation depth for easy monitoring under the protection monitoring concept. Again, please try with any means to perform these electrical conductivity depth profiles. It is much more difficult in this case, since most of times require taking out the pipes in the pump from the abstraction wells. But if you have the chance to do it, please do it. The other thing that I would like to mention is that after the sensor installation, please have a testing period and verify if spikes or flat trends appear in electrical conductivity records, and be flexible to adjust the installation depths. Let's see now some elements regarding the monitoring frequency, a very critical aspect. There are no standardized answers for deciding on monitoring frequency. There are several parameters that have to be assessed, and it is a case-specific decision. In general, we need to balance between high and low frequency, considering that the high frequency monitoring can reveal to us much more detail in the evolution of groundwater salinization processes. But on the other hand, putting too much detail can add a lot of effort on processing time and to understand what's going on behind these measurements. the monitoring frequency increases together with the energy consumption, which is very critical since, as we will see later, for many sensors, there is no option to change the battery, or the battery is very expensive. Moreover, the higher frequency can reveal mechanisms that are not expected with the lower frequency. So the lower frequency can result in missing out these essential mechanisms or effects. Finally, with a high frequency, you have on the spot monitoring of the evolution of the groundwater salinization phenomena. But on the other hand, you need more money to transfer and store your data. These are the four key categories of criteria that can be used in order to define monitoring frequency. The first one is the environment of the aquifer and its surrounding. The second one is the monitoring target involving the problem definition. The third one considers the groundwater wells specifications and status. And last but not least, a key category of criteria involves the monitoring equipment and infrastructure that we have. Andreas, please, and I think that we have to speed up a little.
Okay, I will try to do my best. So, category 1, aquifer system and surrounding environment. What does this mean? It means that we have a natural system, and based on the properties of the natural system, we need to analyze what we're dealing with in order to come up with appropriate monitoring frequency. Start with geometry. The geometry deals with the depth, the thickness of the aquifer, the margins of the aquifer, and so forth. We also have the hydraulic regime, the hydraulic properties, the gradient, the boundary conditions, and the boundary conditions relate to how much water flows in laterally, how much water goes out, how we abstract the aquifer, how we exploit it, what's the recharge the aquifer receives, and so forth, and what are the stressors. And of course, the distance from the coastline. And why all this matter? Because if you have, for instance, a very thin aquifer with very high conductivity, then what you know out of hydraulics is that probably this aquifer will have a very rapid response to any stress imposed on it. So the simplest and the smallest discharge will have an immediate effect on the aquifer and probably a profound change in electric conductivity and or a change in the hydraulic gradients within the aquifer. This means that probably you want a very high frequency in this case. But if you are dealing with a massive aquifer, which is also having a high hydraulic conductivity or high storativity, then chances are that a minimum or a small abstraction imposed on the aquifer will not have a big impact on the response to the conductivity or to the hydraulic gradient. This means that you don't really need to spend resources and collect a lot of data that would not vary from each point to the other, simply because the aquifer will not change its properties so dramatically. Next one, please, Vasilis. Second criterion to category to consider in order to come up with appropriate monitoring frequency is a monitoring target. You have to define the problem. Which is the problem you have to tackle? Why do you set the monitoring network? And this will give you the ultimate answer to the frequency intervals you have to select. And to define this, you need to come up with definite answers as to the water quality and the welfare. Do you want to monitor the water quality of the wellhead? If yes, then probably you need a very high frequency because simply when you start pumping water out of the well, chances are that you are going to have a rapid response to the change of the quality after a specific point, and you need to capture this point. Then again, you might have a huge aquifer and the monitoring point is far away from the coast, in which case, most probably you're not going to be able to capture any changes at all. So you need to know well in advance the geometry and the hydraulics of the area of your aquifer, but also you need to be specific what you want to monitor. And if it's the water quality of the wellhead, chances are you have to go for high frequency. Local, regional scale, seawater intrusion evolution. If you're going for regional scale, seawater intrusion, then chances are that you don't need a very, very frequent monitoring protocol. If you are going for local phenomena, however, maybe you want to go for high frequency to make sure that you're not losing any changes. Correlate water mobilization. Correlate water mobilization relates to water which is saline and it's entrapped in a geologic medium, and this gets mobilized after a rapid change in the hydraulic equilibrium. So probably at a specific point you overdo it with lowering the groundwater level, and this changes the equilibrium with an entrapped saline water body, and then this saltwater body starts getting mobilized and mixing up with your fresh water. So if you need, or if you have in mind that this might happen pretty soon, then you may want to increase the frequency of monitoring to be able to capture the phenomenon. And then again, it has to you have to take into account whether you are going for local or regional scale upconing. Upconing is a very, very delicate and very, very tricky thing. It relates mostly to the exploitation status of the aquifer. Remember that, as I told you before, upconing is the phenomenon of upcoming saltwater body into your abstraction well because you are lowering the groundwater level within the abstraction well. You lower the groundwater level in the abstraction well, this may result in upcoming of salt water in your well. And this is pretty common in islandic environments where you have freshwater bubbles sitting on top of a saltwater body. And there is where you have to be extra careful. And if you're talking about this kind of environment, then probably you need to go for a very, very frequent monitoring exercise in order to make sure that capture the phenomenon in time to disrupt abstraction and save the day. Because when saline water gets into fresh water aquifers, then it's very difficult to come back. Next one, please. Right. Monitoring equipment infrastructure. This relates to the sensors we have. This is the third criterion, and it really relates to the sensors you have. Here you come to another line of thinking, and the line of thinking has to do with the technical specification and technical constraints you have with regard to the sensor. So you need to account for energy sufficiency. If you are in a very remote place, you need to make sure that you select monitoring frequency that will not drain your batteries if you don't have solar panels to drive your sensors, so that you have enough energy to get the monitoring network going for quite some period so that it doesn't run out and get disruption. You also need to take into account the consumables lifespan. And we're talking about the membranes and the electrolytes in the sensors. For instance, if you're talking about the pressure transducer or an electric conductivity sensor, a CPD sensor, then this is not relevant because you don't have any consumables there. But if you have decided to install a pH or an AMP sensor, then you have to be extra careful how often you monitor. There are two different things. One thing is the drifting of the sensor, And the drifting of the sensor has to do with the calibration intervals, and this cannot be overcome. The other thing has to do with the lifespan of the sensors, and the more frequent you monitor, the more you tear and wear the sensor. Okay, so the more the measurements you make, the closer you get to the life end of your sensor when it comes to pH or ORP. So you need to be extra careful when you decide how frequently you monitor, because you don't want to ruin your sensors before their time. Calibration interval requirements. Right. You select again how often you monitor based also on this parameter. What's the stability window? What's the drift slope of this sensor? And what's the response time of the sensor and the outcome? Please have in mind that every time the sensors, especially the ORP, the DO, and the pH sensors, need to make a measurement, they need to trick it, kind of say, in order to do some self-checks, perform the measurements, and then go to hibernation mode and go again. All these things have to do with the stability, the calibration, and the drifting. And you need to be sure that the overall thing gives you the appropriate frequency interval, not overdoing it or losing essential trends of the evolution of the outcome. Last but not least, the maintenance interval requirements. Extra important. There is no need to perform very frequent measurements if you don't respect the maintenance interval requirements. These two have to go hand to hand. Very frequent monitoring with no maintenance, no use at all. In here with the green rectangle, you see the suggested window from two of frequency intervals. Let's go to the other one of Vasilis, the fourth criterion B, which relates to the telemetry. Also very important, because how frequently you are going to monitor relates to the telemetry facilities you have available. Things to consider: the data plan and the cloud platform restrictions and costs. You may be in an area, in a region where your budget is not enough, or the telecommunication costs are extremely high. In this case, you have to be extra careful how often you monitor, or how often you send the data, because monitor the data is one thing, sending the data is another. You may be monitoring very, very frequently and decide that the data are being sent once in a day to save on the data plan. Also, you may have a restriction to the size of the cloud service you are using over the internet, and you want to use a small cloud service, a small cloud volume, and so you need to make sure that you manage the correct way how much data you upload there. The energy sufficiency. The more frequent you collect data and the more frequent you send data, the more energy you consume. The lower the GSM signal in an area, the higher the energy it consumes. You need to be very, very careful when you decide how frequently you monitor and how frequently you send data. Servicing and maintenance and repairs frequency. Also, this relates to telemetry, and you need to be extra careful. Antennas, SIM cards, or the electronic circuitry for the LoRa domain. You are going to be told about this later on. Needs to be carefully considered before you decide on the frequency. And the overall stability and reliability of the system. You may be in an area where the GSM connection is extra reliable and extra strong. But then again, you may be in an area where the signal is marginal or depends highly on the climatic conditions, on The static electricity you have in the atmosphere that may affect the transmission, or how easy it is to connect to the cell of the cellular network, and so forth. You need to be extra careful because every time the system will try to connect to the GSM network, it will consume energy. And the furthest it is, or the more the unfortunate, the unsuccessful connections are, the more the energy it consumes. And this needs to be carefully balanced and calculated when you decide on the telemetry frequency, which again has to do with how often you send the data, not how often you collect the data. And the next one, please, Vasilis. The third category on the monitoring equipment infrastructure has to do with the local storage. If you decide not to go on telemetry, but locally store the data, because telemetry is expensive or it's not available in your area, then you have to come up with all this. How often you have to transport to the area to collect the data in order not to overwrite the data because of high frequency to the memory stick of your sensors. Also, you have to make sure that the roads and the monitoring wells are accessible in a reasonable time domain so that again, you don't come up with oddities and surprises in data integrity on the local storage. Also, it has to do with the servicing and maintenance frequency and the capacity and reliability of the local storage system, which in turn relates to the battery's efficiency and reliability or the solar panel efficiency and reliability. And on top of that, unfortunately, it relates to how safe the area you have installed with the sensors you believe it is. Okay, in terms of any breakages or thefts or so forth. So you put all these parameters down and you decide how frequently you visit the area and how frequently you store the data. Let's go to the next one, Vasilis, which is the last of the criteria.
So nice.
No,
It's my internet. Monitoring is inherently connected to the existence of instrumentation. Hence, maintenance and servicing is needed. Meaningful monitoring requires reliable measurements taken at predefined time intervals under the appropriate conditions, employing a suitable protocol, and of course using well functioning, thus reliable instruments. Therefore, even though an instrumented telemetric monitoring network may have been set up, okay, so we have all of our data in our office remotely, still field operation at frequent time intervals have to be conducted in order to ensure the longevity of the network and its nominal operating conditions. Field operations may be distinguished into two distinct categories: the calibration sequence and the general maintenance, which leads to have a network welfare. So these are some do's and don'ts related to calibration sequence. So you have to use fresh standards. You have to know very well to study the instrument's manual. You have to exercise yourself in the instrument. You will not have time in the field to do it. So do it at your lab and be ready to use it in the field. Of course, the instrument have to be checked for its integrity, and also the solutions that you use for the calibration. Please respect the calibration intervals. Don't, let's say, use only one if you have to use 2 or 3 calibration intervals, especially for pH. You have to make a checklist and have it with you when you go to the field. Sometimes it is pretty far from our office. There are things that we cannot find easily. Moreover, please ensure the temperature equilibration between the sensors and the calibration solution. And of course, we have to check the instrument performance, calibration status, and response time and accuracy. Let's see now some elements of maintenance. The first element is the sensors and probe casing. Normally, maintenance relates to either wear of the contacts of the sensor or scaling or other deposition on the contacts of the sensor. Any of the 2 problems mentioned may be visually inspected. You can see it. Connection cables, where they exist, are vital for the seamless operation of the monitoring network, even though measurements themselves are conducted in other parts of the system, since the cables are usually connect the data logger to the sensor. It is highly recommended that the integrity of all connection cables and the connectors are regularly inspected visually, tested for their integrity, and accordingly cleaned and repaired if and when required. So whether these sensors are installed underwater, at the wellhead, or in open air, extra care should be given to ensure the integrity of telemetric units and data loggers. Depending on where each unit is installed, things to inspect include protection against humidity, which can significantly harm your equipment, the integrity of casing. If housing is soiled or filled with insects, it is a very common problem. And if housing is damaged by animals or vandalized by people, we have seen many times, let's say, the birds or some foxes or some cows damaging the cables and the instruments. It is clearly understood that an energy source is necessary for any instrument to operate and perform the requested program or triggered measurements. So we have to check the status of the battery and be provident and change the battery prior its drain out, since then we will lose data and we don't want this to happen. Finally, the installation facilities included the suspension cables, and gadgets, the sensors, housing, installation gauges, protective fencing, let's say thunder protection, wellhead installation, informative signposting that we have in our monitoring well, and any infrastructure that is directly or indirectly related to the monitoring network. We have to inspect. So we will need, let's say, several hours to discuss on hardware maintenance tips. What we would like to introduce is the human aspect within this hardware world, let's say, thing. So provide the stakeholders that are around your monitoring network and the society with access to meaningful results that will convince them of the significance of the installations and render them potential guards of the system, the hardware, rather than potential vandals. So people have to see that you take your job very seriously. You inform them about what you do and make them feel that they are part of the monitoring process and the very significant results. And then they will definitely support you on keeping your hardware in good shape. So, prerequisites. We need enough experienced personnel of the appropriate skills. We need sufficient administrative structure and freedom to act offered to the staff of the net. We have to carefully estimate all our costs, the operating, the maintenance, the investment costs. We have to also ensure the adequate budgeting. Detailed calibration and servicing schedule has to be compiled and assigned to specific staff members, including coinciding conventional monitoring through sampling and laboratory analysis. And also a time frame for local, regional, and national promotion is needed, and scientific exploitation of the results designed. So, last but definitely not least, the success of the network of a monitoring network design depends upon the clear understanding and definition of the scope of the network out of the numerous key alternatives that we might have. Deciding what we want to monitor for and understanding the particularities of the features we target will define how, when, with, what will be monitored. Hence, defining the scope of the network will guide us to the spatial distribution, the density of instruments, the monitoring frequency, the specifications of the instruments to be used, the actual points the instruments will be installed at, and then we have the 5 fundamental functions in which groundwater salinization should be based on. So we have the aquifer function. An aquifer unit or an aquifer system may be vulnerable to its resource quantity or quality deterioration. Moreover, as a consequence of excessive impacts through its water depletion, it runs a risk of matrix compaction, hence permanent destruction. The second function, specific use. Quite often, the core target of a monitoring network is focused around a specific use. In this context, the maximum allowable parametric values may vary vastly depending on the targeted use. This is why we have to put this function in the game. For example, domestic water domestic water supply, the maximum admissible concentration of nitrates it's 50 milligrams per liter. In the other side, let's say for irrigation purposes, there is no definite limit uh, defined. The soil. The soil is a valuable resource, as you all know, upon which the whole humanity has placed major investment. The soil is exposed in the risks of salinization, erosion, desertification, compaction. So, being the major receptor of water from irrigation, and along with it also high salt content leakage due to fertilization, the soil needs to be function depending on the application and needs to receive sometimes extra attention. Water resources. Apart from the protection of the aquifer for its own, the water resources may also be subject to monitoring for protection, restoration, and preservation. So, water resources may include groundwater bodies and or surface water bodies that are as a whole or partially being recharged by a groundwater body. They are dependent or partially dependent systems, ecosystems. A special case of the previous approach is the ecosystemic approach, which it is clearly described in the Water Framework Directive as the case of terrestrial groundwater dependent ecosystems. So the existence of such ecosystems, wetlands, water bodies, or a mixture of both, depends on the provision of sufficient water volumes of acceptable quality from the linked aquifer system. Let's go now to the alerting setup sequence. At first, we have to define the specific function for which we would like to set up the alert. The next step is to define the alert as it could be either related to groundwater quantity, that includes parameters such as water level, let's say, or related to quality, or both. Sometimes establishing indicators for alerting, it's much more useful instead of applying raw data. Such indicators could be, for example, some ratios of monitored parameter, percentages exceeding threshold, and there are other options too. Then we have to establish the alert levels. How strict or loose a trigger values is to set off an alert depends largely on the policy the decision makers opt for and, of course, objectively relates to the level of protection one seeks to achieve. Beyond this general statement, two main levels of alerting can be found: an early warning and a critical warning. Then we have to define the alert mode to be either automatic or manually. Depending on the risk level related to the alerting situation, we may have to incorporate a kind of confirmation, which can be either remote, or maybe we have to go to the site and make some in situ examination in order to avoid these false, let's say, alerts. The alerting procedure should also include a protocol that define the actions to be made, incorporating soft and hard measures depending on how critical the alerting level is, as well as standardized informing and reporting procedures. Then we also have to closely monitor the evolution of the phenomenon that triggered this alert, sometimes with even higher frequency than ordinary. Ultimately, the alert ends when, for sufficient time, trends of values or indicators um, uh, have been recovered to some acceptable margins, in some acceptable values. This assessment is the product of the aforementioned evolution assessment. So once the normal conditions have been re-established, monitoring frequency may come back to the standard. So Andreas, would you like to do the wrap up?
I suppose I need to say yes.
Yes, and it should be rapid, quick.
I'm done. So, two things. What is and what isn't a monitoring network? Network is a very valuable research, exploration, and management tool that offers valuable information that is unique information for management and assessment cases. It is an infrastructure, however, that needs serious and in-depth consideration and design. And the reason for this is that it is an expensive, very expensive infrastructure investment to install and systematically maintain. It's not only to install, it's also to maintain. These two things should be linked, and you should always keep them in mind. A lot of monitoring networks across the world have failed in the operational mode. They were set up, but never managed to keep it going for a long time. It's an infrastructure that needs dedicated and trained personnel and specific operational protocols. None of these alone is enough. You need to have personnel, protocols, and budget. If any of the three are missing, you don't have operationalization of the network. And what isn't a monitoring network? It's not a panacea for resolving every water management related issue. It doesn't mean that you have a monitoring network with thousands of sensors and millions of data points and trillions of files with huge number of numbers, and you resolved your management issues. No, you need this data to come up with management solutions, but you need to process the data, analyze, and assess. It's not a generic tool to address all monitoring targets. As we said, a monitoring network resolves specific problems. You cannot address every problem with a single network. Not a case, not possible. It is not a self-sustained infrastructure. Unlike what many people think, that you just need to buy the sensors, install them, and just out of magic, it's going to run by itself. It's not the case, guys. You need to spend time, resources, and energy on it. When you install the sensors, then the real problem starts, not before that. It's not an easy to design and run network. There are networks that are a piece of cake, design, install, and run. Monitoring network for groundwater resources is not one of them. Of course, it's not a cheap solution. You need budget. Okay, budget, personnel, protocols, and then you have a good case. Thank you, Vasily.